Okay, so now the next thing to talk about is the relationship between the variables. So with the drilling rock example, we did the scatter plot, then we did the regression line, then we interpreted of what the meanings of those slope and y-intercept parameters mean to the problem. But then, like, how good is that relationship, right? How good is the correlation between the starting depth of which you start to drill rock and how long it takes to drill for 5 minutes through rock, through 5 feet of rock? And so we need to start thinking about, okay, now we could see there's some sort of linear relationship. Now we ask, how good is this relationship? That would be the next process in our thoughts. So let's go ahead and take a look. We could see that this value in which is an indicator to determine the strength of the relationship is called the correlation coefficient. So the correlation coefficient R is just an indicator to determine the strength in the relationship between the explanatory and response variable. The linear correlation coefficient is given by this formula here, which that's crazy. And so you can see why we use technology, because we would have to find the average of our x's, average of our y's, subtract it from observed, divide by the respective standard deviation, multiply them, then add them all up, and then divide by n minus 1. And we're just not going to do that by hand because our goal is not to do arithmetic. Our goal is not to subtract, multiply, and divide. Our goal is to get the results so we can interpret the mathematics into a meaningful conclusion. So we're going to be using the calculator for this calculation. Some property. It's a unitless measure because we're just measuring the strength. The closer it is to -1 or 1, well, I'm sorry, the property 2 is R is always between -1 and 1, and that the positive values of R correspond to positive relations, negative values of R correspond to negative relations. The closer R is to +1 gives a more stronger positive association. And similarly, when R is closer to -1, it gives a stronger negative association. If it is 1, then it's a perfect linear positive relationship. If it's exactly -1, then it's an exactly negative linear association. And then the closer it is to 0, the less likeliness that there is a linear relationship. So just because R is close to 0 and we say it's highly unlikely to have a linear relationship doesn't mean the data doesn't have a relationship. It could just be a different model of relationship, like a logistic relationship, a normal distribution relationship, an exponential relationship. So there's different types of relationships, but the R close to 0 will just tell us whether there's the linear correlation. Okay, so let's go ahead and determine the linear correlation coefficient for R in the drilling example and then interpret it. So we went ahead and already did this in the calculator. It was all that other mumbo jumbo stuff. So if we just go back to stat and go back to calc and run the same linreg as we did before, and hit calculate, we get the same slope and y-intercept, but notice now we're going to talk about the r squared and the r. So let me go ahead and highlight. So the r is going to be the correlation coefficient. R squared we'll talk about in just a minute. So this would be the correlation coefficient. So R is 0.773. Okay, that's the first part. And now let's go ahead and interpret this in context of a problem. So if I drew a number line from -1 to 1, and here's 0, and here's a half and a half, right? 0.5, 0.5. Where is R? Well, 0.77 is about here, right? Is that closer to 0, -1, or 1? Right, you're like, oh, well, it's actually pretty close to 1. Well, if R is close to 1, positive 1, that means it's a stronger positive relationship. And if we go back to our scatter plot, right here, was there a positive linear association? Yeah, right? Rising left to right in that line. And our data, as x increased, y is also increased. So it makes sense that our r was positive because we knew we had a positive association, but also it was a stronger relationship. So let's go ahead and interpret this. There is a strong positive linear relationship between starting depth and the time it takes to drill 5 feet. Okay, so notice that I could say like as a r equals 0.773. But what does it mean to like the world? If I wanted to talk to you about it and I knew nothing about statistics and I was working in a probably a business where the machines I sold was drilling rocks, right? Like what would I say to customers? Oh, you know what? Our machines are hard. Our statistics show that if you buy our machine, that you're going to have as your depth increases, your time here, there's a strong correlation between how long it will take you. I mean, so the data you need to be able to interpret from the math into a conversation. And so the correlation coefficient will just tell you the strength of the relationship, what type of relationship, positive or negative, between the explanatory and response variable. So if we move on, we can talk coefficient of determination. And we talked about this a little bit in the beginning when we talked about explaining like that nothing was causation, right? And I had mentioned that the amount of butter people eat is correlated with the number of divorces. So does that mean the less I eat butter, the less likely I'm going to have a divorce? And recall that this regression analysis is just relationships and correlation. It's not causation, right? One doesn't cause the other. It just means that there's a relationship sitting there. I also mentioned the number of stars in the sky and the number of car accidents. There's a relationship there and the correlation coefficient is high, but it doesn't mean one causes the other. However, if I took the correlation coefficient and squared it, it will now become the coefficient of determination. And that is the percentage of how much the explanatory variable will explain the response variable. So if the coefficient of determination for the butter and divorces example, let's say, was 25%, that means 25% of the amount of butter I eat is explained by, 25% of divorces is explained by the amount of butter I eat. So the R is the correlation coefficient, which will tell us the strength of the relationship. And then when I square that R, it becomes the coefficient of determination, and it'll give me the percentage amount of how much that explanatory variable explains the response. So let's go ahead and look at a couple of properties. So if I square the R and it's close to 1, close to 0, it indicates that there's very little explanatory power. And then if I square it, it's close to 1, we can see that the explanatory variable, it'll be high percentage, and it'll indicate much explanatory power. So because it's a percentage, it only will live between 0 and 1. So if I look above or just grab from the calculator again, this from the drilling model, okay, here's the R squared. So if I went to the calculator and squared the r, you would get 0.597. So if I went over to the calculator and took 0.7728, let's see, let's say 2, and then squared it, notice I get, let's see, where it is. Here it is. I get the r squared, right? 0.59725, pretty close, right? Because I rounded. But essentially all the calculator does for you in this linreg is take the r and square it, and that's what it displays. It's literally r squared. So rewriting this, so let me go ahead and r squared, which is the coefficient of determination, is 0.597. And so that's just the numerical value. And now I need to go to my boss in my drilling rock company and go explain this to him. So then I would say, this means 59.7% is explained by the starting drill depth. Okay, and furthermore, we could even dig deeper, right? So furthermore, 40.3% is explained by other factors. Like, remember, and we mentioned this prior, right? What was one of the lurking variables, right? The density of rock. So like density of rock, machinery, right? If you got a better machine than other people, so machinery. So, when calculating it, the calculations are really quick when you put it in the calculator, but I think students tend to spend a long time on the explanation. So just know that r squared is a percentage, and what it means is, in this case, that we could say that 59.7% of the time it takes to drill 5 feet is explained by the starting drill depth. And furthermore, if I took 100% and subtracted 59.7%, I would get the remainder of 40.3%, right? And that means that whatever's left over, which is 40.3%, would be explained by other factors like the lurking variables, density of rock, the machinery, etc. Okay, and then just to kind of give a warning here, so to determine the r squared for the linear regression model, we just squared the correlation coefficient, right? However, that squaring the linear correlation coefficient to determine the coefficient of determination only works for the linear model. So when I say r squared, it's only for a linear model. If it was any other type like parabolic, exponential, logistic, any other type of model, nonlinear, it wouldn't work. This method doesn't work for everything. It's just the fact that it's linear and the slope is a constant rate of change that we were able to take the r and square it. Otherwise, it doesn't work for all.